Alright, so this very last thing for Unit 7 is colligative properties. Now, back in Chem 1, you might have done the calculations with colligative properties to determine like how many degrees Celsius your vapor pressure would be lowered by, or sorry, not your vapor pressure, your freezing point would be lowered by, or your boiling point would be raised by. You might have done vapor pressure, my kids didn't, but you might have done it with another teacher. They actually just did away with all of the calculations for colligative properties on the AP exam, which is why you don't need to calculate molality. So really with colligative properties, you just need to understand what's going to happen to the vapor pressure, the boiling point, and the freezing point when you add a solute, and a simple explanation as to why. Really, the explanation is way beyond the scope of this course. But then that's another reason why they're moving kind of away from it, because they get really simplistic, dumbed down answers, because that's all that really high school AP Chem kids can understand. So colligative properties are properties that depend on the number of molecules or ions in a solute present. So that depend on the number of molecules or ions of the solute present, and not on what the particles are. So what matters is the number of particles dissolved. So there are three different colligative properties we're going to talk about. There's vapor pressure lowering, boiling point elevation, and freezing point depression. I'm actually going to talk about the boiling point one first, and then that will kind of explain the vapor pressure, and then I'll talk about freezing point. So when talking about boiling point elevation, imagine I have, trying to pick a good color, I have a container of a solute, a solvent. All of the gray is just a pure solvent, okay? In order to boil it, some of those particles have to vaporize. They have to go to the gas phase, right? If I were to add in some solute particles, so I'm going to make them much bigger and in purple. By adding in those solute particles, those solute particles are impedes, I think that's how you spell impedes the solvent from getting to the surface. So now more energy is required to boil the solvent, which is why the boiling point is elevated. Right? Again, very simplistic explanation as to why, but those solute particles get in the way. Right? Which this also leads into why vapor pressure is lowered. Okay? Because, same thing, you add in those solute particles, less solvent particles are going to the gas phase, so the vapor pressure is lowered. So the explanation for both of these ends up being the same, right? Lower boiling point means higher vapor pressure. Higher boiling point means lower vapor pressure. They go hand in hand. Now, with the freezing point depression, the best thing is to, I put the picture here, but this is a picture from earlier in the whole packet. It's really zoomed in, that's why it's a little bit fuzzy here. But see how those water molecules, that's ice, that's solid water. They're nice and neatly ordered, and they're aligned very perfectly. All right, if we throw in these big old solute molecules, I'm just throwing them wherever, that's going to disrupt the nice little alignment that all of those water molecules have made. All right, so now in order to get the ice or the water molecules to align to make ice, you have to decrease the temperature even more. You have to slow down those molecules even more so that maybe those solute particles get stuck in between the ice molecules instead of disrupting the pattern. Right? So you have to slow down the molecules, which means lower the temperature, which means depress the freezing point. Lower the freezing point. Okay? So one thing to think about, an easy way to remember it is, say here is a normal solvent boiling point and freezing point, okay? freezing point being on the low end, boiling point on the high end. Obviously, it's not going to have a higher freezing point than it does a boiling point. Adding a solute to that makes that range higher, or makes that range bigger, right? So adding a solute to a solvent makes it a little bit bigger, like it makes the boiling point higher and the freezing point lower. All right, so it just makes that range a little bit larger. All right, but let's do some examples. Say I have 1 molar glucose, and I have 1 molar sodium chloride. Question is, now this might be an AP question, which solute will have a greater effect on the colligative properties? All right, so the answer is sodium chloride, and the reason why is because it has more ions. Right? Glucose, when it dissolves, it will dissolve. I mean, sugar will dissolve. It only dissolves as one molecule. Right? It doesn't break up in anything because it's not ionic. NaCl will break up into an Na plus ion and a Cl minus ion. That's 2 ions. So this has a greater effect. On the colligative properties. Actually, it's double the effect because here we had 2 things and here we only have 1. All right. One thing I want to point out, I'm going to go back to that. Here on the definitions, it said here that the solutes will affect, the number of solutes will affect the colligative properties as long as they are not volatile. So if you have a volatile solute, like maybe ether being dissolved in the water, it's not really going to have an effect because it's so volatile. It's going to come out of solution so quickly. It wants to be in the gas phase, so it's not going to stay dissolved, and therefore it's not going to make a solution for very long, and it's not going to affect the solvent to the extent that non-volatile solutes will have. Okay. So let's just do another example of comparing 2 different substances and looking at which one will have the greater effect. This time we're looking at 1 molar Na3PO4 and 1 molar NaCl. Well, we already know that NaCl is Na plus and Cl minus. That's 2 ions, or 2 particles. Na3PO4, that breaks up into 3 sodium ions and 1 phosphate ion. That's a total of 4 ions. So the thing that will have the greater effect is the sodium phosphate. More ions, or more particles in solution, mean it's a greater effect. Right? And then some real life examples of this would be, so some things where you actually see colligative properties in action is, I mean, right now we have lots and lots of snow on the roads, and they pre-treat it by putting salt. They can pre-treat the roads by putting salt down, and that will keep the water from freezing on the roads. Or if you already have frozen, like, if you have a sidewalk that already has a solid block of ice, you can put some salt on it, and depending upon the temperature, that salt can disrupt the pattern and can melt the ice. Again, it's all temperature dependent, and it depends on how much salt you put down. I mean, obviously, if it's cold enough, the pre-treatment won't work, which we saw a few weeks ago. So it depends on temperature, but it generally helps. But that's an example of lowering the freezing point. Another example is in your car, you have antifreeze in your radiator, which during the winter months, especially further north from here, but during the winter months, it helps keep your radiator from freezing, the water that's in your radiator from freezing and then cracking and then spending lots and lots and lots of money. In places where it's really warm for an extended period of time, like down in the south, we really don't have to deal with this too much. But antifreeze will also help keep it from boiling. It'll help as an anti-boil. For the same reason, if you add that ethylene glycol, which is what antifreeze is, if you add that to the water in your radiator, if you put antifreeze in there, it'll not only keep it from freezing in the winter months, but it will also help it from boiling in the summer months, because you are increasing that range between freezing point and boiling point. Another example is when you cook, you put salt in water. When you want to like make pasta or something like that. One of the biggest misconceptions is that the reason you do this is to make the water boil faster. But we know that that's not true, because you're increasing the boiling point. It's boiling point elevation. You're increasing that boiling point. So actually, it's going to boil the water slower, but it'll cook the pasta faster. And people put salt in water to season it. Same thing if you were to put oil in water. Even though oil doesn't really dissolve in water that much, it still will help disrupt and keep some of those water molecules from escaping to the gas phase. So some people use oil, some people use salt, whatever. So, but yeah, salt and water does not make the water boil faster. It makes it boil at a hotter temperature, which obviously is going to take longer to get to, but it'll make the pasta cook faster. All right. So, like I said, no calculations on the AP exam for this stuff. They'll be asking you questions like this for you to compare substances and say which one's going to have the greater effect. I don't even think they're going to ask you to explain why these colligative properties occur. Just know what the three things are. That is vapor pressure lowering, boiling point elevation, freezing point depression. It helps if you understand why a little bit, though, because it'll help you remember which ones they are. All right, and that's it for Unit 7. Yay!